Welcome to the Depth Dive. Today we're taking a close look at something that seems pretty simple in metal casting, but can actually cause some surprisingly tricky problems.
That's right. We're talking about the sand itself, specifically in green sand casting.
Exactly. Our goal here is to really understand how controlling the properties of, well, this foundational material is just absolutely crucial for dodging defects and getting those quality castings.
Think of it as getting down to, the bedrock of the whole process. We're going to explore how little variations in that sand mix can lead to a whole bunch of issues.
And importantly, how foundries can actually take control, right? By understanding and managing those properties with the right approach and the right tools.
Precisely. And we're drawing on a lot of established knowledge here. The industry's been looking into this for a long, long time.
Yeah, the history of seriously studying foundry sands goes way back. Over a century, actually.
It really shows how fundamental sand control is. It's been a cornerstone for ages.
Okay, so let's dig in. How does this mix sand, clay, water, how does it actually cause defects in the final metal part?
Well, a lot of it comes down to the mechanical strength of the sand at different points, when it's green or moist, when it's dried out, and critically when it gets hit by that intense heat from the molten metal.
Right, so if it's not strong enough at any of those stages,
then you've got problems. Low strength means the mold might not hold its shape properly, or it might not stand up to the metal pouring in. That can mess up dimensions, even cause weak spots in the casting.
Okay, so low strength is a big one. What else about the sand causes trouble?
Beyond just strength, the actual composition is vital. Like too much moisture in the mix, that's a classic trigger for defects.
Too wet.
Yeah. And also a high amount of volatile matter. So anything in the sand that turns into gas when it gets hot, that can create big issues inside the mold cavity.
Gas issues. Yeah, I can see how that would lead to things like porosity, bubbles in the metal.
Exactly. Trapped gas is a major headache. And think about a defect called open grain structure.
Open grain. What's that look like?
It means the casting looks really coarse, kind of rough, after you machine it or if it fractures. And surprisingly, that can often be traced right back to too much moisture in the sand.
Really? How does extra water cause that?
Well, if the sand's too wet, it doesn't compact properly against the pattern. You get a less dense mold surface, and that can actually influence how the metal solidifies, leading to that coarser grain.
Wow. So too much water impacts the actual metal structure. That's quite a link. What about surface flaws? Things like scars, seams, and plates. Is sand involved there too?
Oh, absolutely. Those kinds of imperfections where the casting surface isn't smooth or doesn't quite match the pattern. Yeah, molding sand issues can definitely be a contributing factor. Inconsistencies in the sand, how it packs.
Okay. And pushes. Those raised bits you sometimes see, I remember hearing those are about how the mold's supported.
That's right. Pushes often point to instability. Like the mold bed wasn't quite right, or maybe there were hard lumps of sand packed in there. The metal pressure finds those weak spots and pushes the sand out.
So uniform packing and support are key there.
Definitely. It highlights why consistent sand properties and careful mold prep are so important.
And then there are drops. That sounds pretty literal, like sand just falling into the mold.
Exactly what it sounds like. Drops are a classic sign the sand isn't holding together properly.
What causes that? Just weak sand?
Usually, yeah. Not enough strength or cohesion. Could be not enough clay binder. Maybe it wasn't rammed hard enough when making the mold. Or even just vibrations shaking bits loose. The sand structure just gives way.
I can imagine that causing major scrap. A chunk of sand in your casting.
Yeah.
Not good.
Not good at all. I've seen foundries lose whole batches because of what seemed like a minor sand cohesion issue. Prevention is way, way cheaper than rework.
Okay, so we've clearly established sand properties are critical. How do foundries actually get a grip on these properties? How do they keep things consistent?
Right, the cornerstone here is testing. Rigorous testing and evaluation of the sand mixture. That's where the industry standards, the established procedures come in. They give foundries the actual data they need.
So it's not just eyeballing it. There are specific tests. What are some key ones? What do they tell you?
Well, one of the most basic but critical is moisture determination. We talked about how important moisture level is, right?
Yeah, too much or too little.
Exactly. So there are standard ways to measure it precisely. Knowing that exact moisture percentage is essential for balancing strength and moldability.
Makes total sense. What else?
Clay content. That's another big one. Clay is the binder. It gives the green sand its stickiness, its strength. So tests measure how much active clay you've got in the mix.
Got to have enough glue, basically.
Pretty much. Enough to make a sturdy mold.
Okay, so moisture and binder checked. What about testing the strength itself? How's that done?
There are standard tests for that too. They measure the sand's strength when it's green moist and also when it's dried. Things like shear strength, splitting strength.
Shear and splitting. What does that tell you directly?
It directly tells you how well the sand will resist being pushed around or pulled apart. So its ability to hold the mold shape against the force of the metal. It's your main defense against those drops we mentioned, or the mold walls collapsing. Higher strength generally means a tougher mold.
Got it. And what about the gases? You mentioned gases being generated. How do they make sure those can get out?
That's permeability. Permeability is just a measure of how easily gas can flow through the sand mold.
Right, like how breathable the sand is.
Exactly. It's critical for preventing gas defects. If the gases from the metal hitting the moist sand or from binders burning off can't escape through the sand pores, they get trapped in the metal.
Oh,
so
wow.
you test the permeability.
Okay. We also hear about the AFS grain fineness number. Is that a test?
It's not really a test procedure itself, more like a calculated result. It comes from doing a sieve analysis, shaking the sand through stack of screens with different mesh sizes.
To see how fine or coarse the sand grains are.
Precisely. The GFN gives you a single number that summarizes the overall particle size distribution. It affects the final surface finish of the casting and also influences that permeability we just talked about.
Okay. And last one, what about those volatile materials you mentioned earlier?
Right. There are tests for volatile material content and also loss on ignition, or LOI. These basically measure how much stuff in the sand mix will burn off or vaporize when it gets really high.
And high values there mean?
High values mean potentially more gas generated during casting, which increases the risk of gas-related defects. It's a flag to say, hey, maybe adjust the mix or the additives.
Okay, wow. So to do all these different important tests, foundries must need quite a bit of specialized equipment, right? What kind of gear are we talking about?
Oh, absolutely. You need the right tools for reliable results. For moisture, maybe a precision balance in a drying oven, or perhaps one of those rapid infrared moisture testers.
Okay.
For clay content, you often see things like a rapid sand washer, maybe an automatic clay determination unit.
And for the strength tests?
You need specific machines, shear strength testers, tensile testers, splitting strength apparatus, and crucially, to make the little sand pucks for testing, you need a standard sand rammer and specimen tubes. Can't do much without properly prepared samples.
Right. Consistency starts at the sample prep.
Definitely. Then you need a permeability meter for checking gas flow. For the grain fineness, you need that set of standard testing sieves and a mechanical sieve shaker. Hot strength testing needs special furnaces and loading frames. It adds up.
That is quite a list. It really sounds like investing in good quality equipment is non-negotiable if you want accurate data.
It really is. You need gear that's high-end, reliable, durable, and maybe most importantly, offers high precision. If your measurements are off, your adjustments will be wrong, and you could actually make things worse.
Yeah, garbage in, garbage out.
Exactly. And, modern testing equipment is often IoT connected now.
So it talks to the network.
Right. It automatically logs the data, sends it where it needs to go. That means that the lab techs or engineers can spend less time writing down numbers and more time actually analyzing the results and figuring out how to optimize the sand system.
That makes sense. Focus on the analysis, not the admin.
Precisely. And companies like Versatile specialize in providing this kind of comprehensive range of high-quality, connected sand testing equipment built for the demands of the foundry floor.
So leveraging that kind of tech helps move towards really data-driven sand control.
It absolutely does. And, for foundries looking for a really integrated, efficient solution, there's even the option of a fully automated sand lab basically packed into a single box, sometimes called a black box system.
A whole lab in a box.
Yeah, pretty much. These systems can run a whole suite of standard sand tests automatically with minimal operator input. It's a very streamlined approach to getting comprehensive sand data quickly and consistently. Versatile offers these kinds of advanced black box systems too.
That sounds like a major efficiency boost for quality control. Now, beyond just having the gear, are there key best practices foundries need to stick to for sand testing?
Oh, definitely. Even with the best equipment, you need good practice. Number one is getting a representative sample. The small amount you test has to accurately reflect the condition of the entire sand batch or system. That's critical.
Makes sense. What else?
Regular calibration of all the equipment. You need to know your measurements are accurate, traceable back to standards. That's fundamental.
Keeping the instruments honest.
Exactly. And finally, safety. Always. You're working with machinery, sometimes high temperatures with hot strength testing, potentially dusty materials. Following safety protocols is paramount.
So it's really the whole package. the right tools, using them correctly, following standard procedures, and always prioritizing safety and accurate sampling.
That sums it up perfectly. By really focusing on understanding and controlling their sand through that thorough testing with reliable equipment, metal casters can seriously cut down on defects related to sand and consistently hit those high-quality marks.
This has been really eye-opening. Taking something like sand, which seems so basic, and seeing just how much precision and control is involved.
It is fascinating, isn't it?
Yeah.
You realize that achieving high-quality castings relies on deeply understanding and managing every input, even the seemingly simple ones like sand. It really underlines the science and engineering involved.
So I guess the big takeaway for our listeners today is that actively managing your sand properties isn't just a nice to have, it's fundamental. You need that testing. You need the right equipment.
If you want to minimize those sand-related defects and maximize your casting quality, investing in reliable, advanced tools like the high-precision connected equipment from Versatile or even those automated black box labs really empowers foundries. It lets them shift focus from just collecting data to actually using that data for smart process optimization.
Which ultimately leads to better castings and efficiency.
Absolutely. And maybe it leaves us with a question for everyone listening.
Go on.
Well, considering just how much complexity we found hidden in something as basic as sand, what other simple parts of your casting process might be hiding similar complexities? What other variables, if you dug deeper and controlled them better, could unlock significant improvements in your results?
That's a great thought to end on, looking for those hidden variables everywhere. Thanks, this has been incredibly insightful.
My pleasure. It's a critical topic.